Okay, good afternoon, everyone. For this afternoon's talk, it's a pleasure to welcome Lukas Bundrock from the University of Alabama. And he's going to tell us about the behavior of absorbing and generating P-log and eigenvalues found in the exterior domains.
Thank you very much. Welcome along, everybody. First things first, I would like to thank the organizers as well as the Isaac Newton Institute for making all these workshops possible and for giving me the opportunity to present our work here today. And most of the results that I would like to show you today are part of a joint project with Tiziana Giorgi and Robert Smits from the University of Alabama. And at this point, I also have to give some credit to Robert for the slides because I basically just copied the title slide, including this simulation in the background from one of his talks. And at the end of today's talk, I will come back to this simulation and I will try to explain how this is related to the mathematical problem that we've been studying, which is an eigenvalue problem of the P-Laplace operator under Robert-type boundary conditions. For short, we just call this P-Robert eigenvalues, and we studied this problem in bounded as well as in a certain class of unbounded domains. If time permits, I would also like to show you some of the results that we obtained for unbounded domains, but the focus of today's talk will be on the bounded setting. I would like to start by recalling the definition of the P-Laplace operator, which is the following one. For a real number p greater than 1, we denote the P-Laplace operator by delta subscript p, and it's defined as the divergence of the magnitude of the gradient of u raised to the power of p minus 2 times the gradient of u. So if p equals 2, the P-Laplace operator just coincides with a classical Laplace operator. For any other p, we have a nonlinear operator. For instance, if p is between 1 and 2, then we have a singular operator because this factor here blows up when the gradient of u is small. If p is greater than 2, we have a degenerate operator. So in any ways, it's nonlinear unless p equals 2. Because of this nonlinearity, we should be a little bit careful when talking about the essential or the discrete spectrum. I would just avoid the term spectrum completely when I talk about this operator. And instead, we defined an eigenvalue in the following straightforward way. Suppose you have a domain omega, which is a subset of Rn. N is at least 2. The boundary of omega is Lipschitz continuous. And we denote the unit normal, which points out of the domain omega by nu. And we do have a real number alpha, which could be positive or negative or 0, it doesn't matter, and a p which is greater than 1. Then we consider the following PDE, where minus the P-Laplacian of u equals lambda times the magnitude of u raised to the power of p minus 2 times u inside of our domain. And on the boundary, we have the condition that the magnitude of the gradient to the p minus 2 times the derivative in direction of the outer unit normal, denoted by partial subscript nu u plus alpha times the magnitude of u raised to the power of p minus 2 times u has to vanish. And then we call a number lambda an eigenvalue of this P-Robert problem if there exists a non-trivial function u in the function space W1p such that the pair of lambda and u solve this PDE. Again, when p equals 2, this just reduces to the standard PDE that you consider when you study the Robert eigenvalue of the classical Laplace operator. If p equals 2, we just have the negative Laplacian of u equals lambda times u inside of omega, and on the boundary, the derivative in direction of the outer unit normal plus alpha times u vanishes. But for a general p, we have to add all those factors, the magnitude of u to the p minus 2 or the magnitude of the gradient to the p minus 2 to account for the nonlinearity. So those factors are chosen such that whenever u is an eigenfunction associated to lambda, then any multiple of u is an eigenfunction associated to the same number lambda as well. And we would like to study how the eigenvalues, or the lambdas, depend on the boundary parameter, on alpha, how they depend on the shape, the geometry of the domain, and how they depend on p. To this end, it would be nice to have a variational characterization of the eigenvalues, and at least for the first eigenvalue, we do have such a variational characterization. The first eigenvalue, if one exists, can always be written as the infimum over all functions u and w on p of this Rayleigh quotient right here, the alpinum of the gradient raised to the power of p plus alpha times the magnitude of u to the p integrated over the boundary divided by the magnitude of u to the p integrated over omega. And many properties that hold true for the first eigenvalue of the classical Laplace operator carry over to the first eigenvalue of the P-Laplace operator. So for instance, this infimum, in fact, is a minimum. The function where the minimum is attained is an eigenfunction associated to lambda 1. The first eigenvalue is simple. The associated eigenfunctions of constant sign, and so on. We completely focus on the first eigenvalue, so we can always use this variational characterization. However, I would like to add one sentence about the variational characterization of higher eigenvalues, because this is where the difference between the p-Laplace operator and the classical Laplace operator becomes a little bit more interesting. If we have, let's say, a bounded Lipschitz domain, then existence of the eigenvalues is not a problem, and in fact we can write down a sequence of variational eigenvalues that tends to infinity. And this sequence does not necessarily yield all eigenvalues. So if you would write down the quote-unquote variational characterization of the second eigenvalue, this is not necessarily the second eigenvalue. It's possible that you miss some eigenvalues. So this is where you got to be a little bit careful, but for the first eigenvalue, if one exists, we always have this variational characterization right here. And most of the results that we obtained are based on finding some estimates for this Rayleigh quotient right here. Before I will show you any of the results that we obtained, I would like to motivate the study of the p-Laplace operator by showing you that it's not just a technical generalization of the classical Laplace operator, but there are actually some applications that occur kind of naturally in physics for the p-Laplacian.
Is there a simple way to explain why the first eigenvalue is simple?
A simple way to explain.
The simple way to explain why is this simple?
I cannot give you one from the top of my head. It is written down in one of these two papers here. I will take a look at the papers later more carefully, and maybe we can talk about this tomorrow. But
for just usual Laplace, it's got a very simple fact that follows from linearity.
Yeah, this
Linear combination is also, but here there's no
linearity. Yeah, absolutely. As far as I remember, it's not a simple proof, but
Okay.
yeah, we can come. It's a fact. It's a fact. Yeah. Okay. So for the classical Laplace operator, there are, of course, many important applications. Among the most important ones, probably the study of diffusion processes. So if you want to study, for instance, how heat spreads out over time, this typically leads to a PDE involving the classical Laplace operator. So if you have, I don't know, maybe let's say a plate denoted by omega, and you want to study how the heat spreads out in this plate over the time, then this would lead to a PDE of this form right here, when U denotes the temperature at the time t and at the point x, so x is the spatial coordinate, then U would satisfy the classical heat equation, which is that the derivative with respect to the time is the same as the Laplacian in the spatial coordinates of U. And then we have some boundary conditions. Of course, they depend on the scenario that we consider. If there is active cooling or healing on the boundary of the plate, you might want to use Dirichlet boundary conditions. If it's isolated perfectly, you would use Neumann boundary conditions. If it's something in between, you might want to use Robert-type boundary conditions like I've written down right here. And then typically, additionally, you know the temperature distribution at time 0, and then you have an initial value problem that can be solved. And PDEs of this type occur whenever we study diffusion processes where the flow is linear. However, there are also applications where the flow is non-linear. For instance, if you consider non-Newtonian fluids, which by definitions are fluids where the viscosity or the thickness changes if you apply a force, then you would get some PDEs of this form with a p-Laplace operator instead of the classical Laplace operator. So everybody's favorite example for a non-Newtonian fluid would be ketchup. Ketchup is what's known as a shear thinning fluid. So if you apply a force, then ketchup gets thinner. This is the reason why if you have a bottle of ketchup, after shaking the bottle, typically it gets easier to pour the ketchup out of the bottle. Of course, there are also shear thickening fluids where the fluid gets thicker if you apply a force, for instance, cornstarch. And if you just imagine a flat surface and you have a bump of ketchup on this surface and you want to study how this spreads out over the time, then this would lead to PDEs similar to the one that we can see at the top with the p-Laplace operator instead of the classical Laplace operator. So there are actually applications for the p-Laplace operator, and this hopefully motivates a little bit the study of properties of these operators. Another application I would like to show you, unfortunately, only works for the classical Laplace operator, but I still would like to show this because I really like it and it's useful to explain certain things that we will observe later. If you think about the following stochastic process where you have a domain omega, and inside of omega you have a Brownian motion, let's say just a particle which moves around randomly. And this particle moves around randomly until it hits the boundary. And when it hits the boundary, we have a branching of particles. Depending on the sign of alpha, either we absorb particles or we generate new particles. In our notation, a positive alpha would be the classical diffusion absorption case. So here, when a particle hits the boundary at a certain probability, depending on alpha, a particle is absorbed, gets killed, it dies, it vanishes. And when alpha is negative, we are in the so-called superconducting regime, where new particles are created, once again at a rate depending on alpha. So when alpha is 0, we generate 0 new particles, and when alpha tends to negative infinity, then the rate at which we create particles tends to infinity. And in this case, the expected number of particles inside of omega can be related to the eigenvalues of the Laplace operator under Robert-type boundary conditions. To be precise, we can interpret negative lambda1 as the growth rate of particles arising from branching of Brownian motions with respect to the local time and the splitting rate negative alpha. So what it means is that when alpha is negative, then we have a positive splitting rate, so we create particles, the number of particles is increasing, and when alpha is negative, lambda1 is negative as well, so in this case we have a strictly positive growth rate, and well, if alpha is positive instead, we would have a negative splitting rate, which means we absorb particles at a certain probability, and in this case lambda1 would be positive as well, so we have a negative growth rate. Okay, I will come back to this interpretation later to explain certain things that we can prove. But our goal was to study how lambda1 depends on alpha, how it depends on p, and how it depends on the domain omega. And I would like to start by recalling some results that are known concerning the asymptotic behavior of lambda1 when alpha tends to infinity, negative infinity, or when alpha is close to 0. To this end, I will assume that the boundary of the domain omega is of the class C1. This is not necessarily for all the statements that I will write down, but for some of them we have to assume that it's of class C1. There are similar results if we only assume Lipschitz continuity of the boundary. On the right-hand side, you can see a picture where I plotted lambda1 depending on alpha if omega is the two-dimensional unit disk and p is equal to 2. And we can more or less see what's going on here that holds in general. So when alpha tends to negative infinity, lambda1 tends to negative infinity as well, and the precise asymptotic behavior is given by minus p minus 1 times the absolute value of alpha raised to the power of p over p minus 1 plus n minus 1 times the maximal mean curvature of the boundary of omega times alpha plus some terms of lower order. There are many papers I could mention. This formula is taken from a paper by Kowarek and Pankrashkin. There are, of course, many other papers in this context, among them a paper by Freitasch and Krajciewicz from the year 2015. And it's worth noting that this asymptotic expansion holds for bounded as well as for unbounded domains. All they have to assume that the boundary is nice in the sense that the boundary is of the class C1 and compact. So if we consider domains that are, for instance, the complement of a compact set, we still have this asymptotic expansion. Of course, here we have to assume that the boundary is of the class C1, otherwise it makes no sense to talk about the curvature. But if you only assume Lipschitz continuity of the boundary, you still have an asymptotic expansion with the same leading term, so with the same minus p minus 1 times the absolute value of alpha to the power of p over p minus 1. Now, I would like to try to explain why the linear term depends only on the mean curvature, only on the maximal mean curvature, and not on any other geometric features of the domain omega. What I'm saying now is far away from being rigorous, and it's just a really, informal explanation, but I still think it might be helpful to understand why the linear term does not depend on any other properties of the domain omega. So if p equals 2, and we have a negative alpha, then, as I said before, we can interpret negative lambda1 as the growth rate of the number of particles arising from a branching of Brownian motions. So if you consider a domain omega, which looks roughly like this, p equals 2 and alpha is negative, then the maximal mean curvature of this domain would be somewhere here on the left side. And if you compare the two scenarios where a particle hits the boundary somewhere around here and a particle hits the boundary somewhere around here, you will observe the following. Let's say we have a Brownian motion which hits the boundary and then new particles are created. course, depending on alpha, we create more or less particles. Then it could happen that a particle hits the boundary again within a really short period of time, but it could also happen that a particle starts to go away from the boundary, and it might take a while until it comes back and creates new particles. In contrast, if we have a particle which hits the boundary somewhere around here where the curvature is huge, and once again we create new particles, then most likely all of the particles that are created will hit the boundary within a really short period of time again. Because if you zoom in locally, all that matters is the curvature, and if the curvature is huge, it's really hard for the particles to escape this part of the domain. So for that reason, the creation of particles that's going on right here dominates the generation of particles that's going on anywhere else. And this would be one way to think about the following asymptotic expansion. Of course, this only works if p equals 2. The result is true for a general p, but I thought it might be helpful to think about it in this way. The second regime that's of interest is the asymptotic behavior when alpha tends to plus infinity. Here in the picture, you can see that lambda 1 approaches a finite limit, and this finite limit is always given by the first eigenvalue of the P-Laplace operator under Dirichlet boundary conditions. It's a super simple proof, and it's not that easy to find a reference for this because it's, I guess, one of the results which is too easy to write it down. So I found one paper by Hilbert in the 80s who wrote it down for the classical Laplace operator, but exactly the same proof works for any p. And then the last regime that's of interest, and this is probably the most interesting one for us, is the behavior when alpha is close to 0. It can be shown that, well, first of all, it's easy to see that lambda vanishes when alpha tends to 0. So the interesting question in this context is what happens with the ratio lambda 1 divided by alpha. And it can be shown that this converges to the ratio of the perimeter of omega and the area of omega. And, well, I'm always saying perimeter and area, but exactly the same works in higher dimensions as well. There are 3 papers I would like to mention in this context. The first 2 papers only study the classical case, the classical Laplace operator. The last paper, which was published recently, also studies the P-Laplace operator. The first paper is one by...
What assumption on smoothness do you need for all the 3 statements? Probably for the first statement you need something like C2 or close to C2.
I think you only need to make sure that the curvature is defined almost everywhere because you take the essential maximum of the curvature.
Okay, and then it's going to be asymptotic, so an estimate of the essential maximum that is not assumed.
Let me answer the first question first. So for the first part, I think it's enough to have C1 or maybe C1 alpha continuity of the boundary. I think C1 might be enough. For the second part, we only need Lipschitz boundary, and for the third part, Lipschitz continuity of the boundary is sufficient as well. Of course, I mean, the entire problem is only well defined if we have Lipschitz continuity of the boundary. Or I guess you could even go a little bit to slightly rougher domains if you talk about the epsilon cone condition, but Lipschitz continuity is among the most general assumptions that you can make. And for the second and third one, Lipschitz continuity is sufficient. If you only have Lipschitz continuity, you can still prove that when alpha tends to negative infinity, that the same leading term asymptotic is true. But you have this linear term, you have to assume that the curvature is defined almost everywhere. So you need a little bit more smoothness.
So this asymptotic expression for small alpha, I guess this is always an upper bound because that's the value you get when you take u to be constant in the variation that's shown.
Absolutely. The upper bound is basically trivial. The lower bound is the one that's of interest. Okay, so the first paper is a paper by Sperb, who studied the classical Laplace operator if alpha is positive, and he basically showed that this asymptotic expansion is true when alpha tends to 0 from above, and he did this by establishing quantitative inequalities that have the correct asymptotic behavior when alpha tends to 0. As you said, the upper bound is for free, but the lower bound is the one that's of interest. Then, roughly 35 years later, Georgi and Smits used a similar idea as Sperb to extend these results to negative alpha. So they found quantitative inequalities that are valid whenever alpha is negative, and that once again have the correct asymptotic behavior when alpha tends to 0. So combining these two results implies that lambda 1 divided by alpha converges to the ratio of the perimeter of omega and the area of omega, if we talk about the classical Laplace operator. And then recently, in 2026, there was a paper by Barbato and Della Pietra who showed that the same limit property holds true for a general P. However, their proof is based on the fact that the eigenfunction converges to a constant, and therefore they get this limit statement, but they do not, or it remains open to find quantitative inequalities with the correct asymptotic behavior, and this is where our research started. So our goal was to use methods similar to the one that Sperb used and Giorgi and Smits used in 2007 to find quantitative inequalities with the correct asymptotic behavior that are valid for a general P and hopefully valid if alpha is positive and negative. Before I will tell you which method we used, I would like to start by showing you one of the results that we obtained when alpha is negative in this setting. So the assumption is that omega is a subset of Rn, which is a bounded domain and has a Lipschitz boundary, and then we can define a constant which depends on omega and on p, but obviously it does not depend on alpha. And this constant is defined as the supremum of all functions w in the function space w1p, and we restrict to those functions where the mean vanishes, so the integral of omega of w integrated over omega has to be 0, and we take the supremum of this fraction right there, the absolute value of w raised to the power of p integrated over the boundary divided by the absolute value of the gradient of w integrated over omega. So because of the vanishing mean property, this supremum is always finite, otherwise it would obviously be infinity. But if we define it like this, we get a finite number which depends on p and on omega. And then we can show the following inequalities. If p is greater than or equal to 2 and alpha is negative but sufficiently close to 0, sufficiently close can be quantified as follows. Alpha has to be between negative 2 to the p minus 2 divided by p times the constant c and 0. Then we can show that lambda 1 is bounded from below by alpha times the perimeter of omega divided by the area of omega plus a certain remainder. And the remainder, we don't have to take a look at all the constants carefully, but what's interesting is the order of the remainder, and this is something like alpha times the absolute value of alpha to the power of 1 over p minus 1. And then everything else is just a constant. Technically, you also have an alpha right here under the square root, but when alpha tends to 0, the square root converges to a constant depending only on p and on omega. So basically, we have a lower bound with the correct leading term asymptotic, and then a remainder that behaves like alpha times the absolute value of alpha to the power of 1 over p minus 1. And we get really similar inequalities if p equals 2 or if p is between 1 and 2. The constants just change a little bit. If p equals 2, we can sharpen the constants, which leads to this inequality right here, but it still has the same structure. The leading term is the same, and then we have a remainder of the form alpha squared times this constant right here. And if p is between 1 and 2, we get almost the same inequality as in the first case. You just have to replace 2 to the p minus 2 by 1.
Don't interrupt it. One more time. This constant is what capacity. Do you have any estimate on this constant?
I think it can be related to Steklov eigenvalue, which of course is not super helpful. For the disk, we can compute it explicitly. For a general domain,
Can it be related to some geometry?
we haven't studied this problem. I would guess somehow. I'm sure it can be related. Because this would make the entire lower bound a little bit more convenient. Yeah, I see the point, but we haven't tried to do this. Okay, so as far as I know, those are the first inequalities that hold for a general P and have the correct asymptotic behavior when alpha tends to 0. But another thing that's of interest, that might be of interest, is that the result that we obtained when P equals 2 is an improvement compared to results that were established before. So some of the adjustments we had to make to the proof, some of the workarounds we had to find, also allowed us to come up with a stronger inequality for the classical Laplace operator than the one that has been established before. To illustrate this, I would like to show you the following picture. Here I compare the lower bound that we obtained, so exactly this lower bound right here, with the lower bound that was obtained by Georgi and Smits in 07. And I compared these two lower bounds for the two-dimensional unit disk when p equals 2, because the result of Georgi and Smits only applies when p equals 2. And our lower bound is illustrated by this blue line. The lower bound obtained by Georgi and Smits is illustrated by the red line. I divided both of the lower bounds by the absolute value of alpha so that we can see what's going on here. And obviously both lower bounds have the same limit when alpha tends to 0, because they have the same leading term in the asymptotic expansion. But there is a difference in the remainder. And it's not just a difference in terms of the constants, there is actually a difference in the order, because our remainder is of the form alpha squared, while the remainder in Georgi and Smits is of order alpha to the power of 3 over 2. So there is a somewhat substantial improvement even to the inequality for the classical Laplace operator. But I guess the most interesting part is that these are new inequalities for a general P. Okay, I would like to show you roughly what the idea of the proof is. And the idea of the proof is based on the paper that was written by Sperb in the 70s. And his idea is that any function u, in his case any function u in h1, for us any function u in w1p, can be decomposed in the following way. We define h as the average value of u, and we define w as u minus h. So u can always be written as a constant plus a function that has vanishing mean. And, well, a few observations. First of all, the gradient of u is the same as the gradient of w, because h is just a constant. The second thing we will need in the proof is a consequence of Jensen's inequality, which states that if we integrate the absolute value of u over omega, u to the power of p integrated over omega, this is bounded from below by the area of omega times h to the power of p, where h is just the mean of u, and some convexity inequalities that hold for any non-negative numbers a and b. So we can always estimate a plus b to the power of p against something like b to the power of p plus a constant times a to the power of p plus a mixed term of the form a times b to the power of p minus 1. And now, using these three facts, we get the following lower bound for the first eigenvalue. The first eigenvalue is just the infimum of all functions u and w1p of this Rayleigh quotient right here. Now, the first step is to use that the gradient of u is the same as the gradient of w. That should be pretty simple. Now, what's more interesting is that since alpha is negative, we know that lambda 1 is negative as well. So we are only interested in the setting where the Rayleigh quotient is negative. So for that reason, if we replace the denominator by something which is smaller, the entire fraction gets smaller as well. So we can replace the denominator by the area of omega times h to the power of p. This is just Jensen's inequality right here. And then the last step would be to replace the boundary integral by something which is bigger. Since alpha is negative, once again, this yields a lower bound. And in the first step, we can use that the absolute value of u is by the triangle inequality bounded from above by the absolute value of h plus the absolute value of w. And then we can use these convexity inequalities right here to estimate this against h to the power of p plus a certain constant times w to the power of p times this mixed term right here. Now, if you consider the terms that are independent of w, which is essentially alpha times h to the p integrated over the boundary in the numerator and the area of omega times h to the p in the denominator, this yields the correct leading term in the asymptotic expansion, and then all the remaining terms are written down in this second fraction right here. And what remains to be done now is to find a lower bound for this second fraction, and this lower bound should behave like alpha times alpha to the power of 1 over p minus 1. What we can do is, we can say, since h is a real number, and let's say we fix a function w such that the mean of w is equal to 0, then this fraction right here depends on h in the following way. When h tends to infinity, obviously this fraction tends to 0 because the denominator behaves as h to the power of p, while the numerator is of order h to the power of p minus 1. Furthermore, alpha is negative, so if h is large enough, then the numerator will become negative as well. So we know that we are negative at some point, and then we are going to 0. Furthermore, when h tends to 0, this entire fraction tends to plus infinity, because we've chosen alpha such that the sum of the first two terms is always positive, and then if h is small enough, the numerator will be positive, the denominator tends to 0, so here this fraction tends to infinity when h tends to 0. So for that reason, there exists a certain h which minimizes this fraction, and finding this h is pretty easy since h is a real number, so you can just use the calculus 1 methods, and this h which minimizes this fraction depends on w, but this can be written down explicitly, and if we just replace h by the h which minimizes this expression, we do have a fraction that depends only on w and is independent of h, and from there on it's pretty simple to find a lower bound that is uniformly, because all we have to do is we have to use Hölder's inequality, and then we immediately get a lower bound for this fraction right here. So this would be the strategy how you can get lower bounds with the correct asymptotic behavior. And maybe if you want to think about this in a bigger picture, the strategy can also be seen as follows. If alpha tends to 0, the eigenfunction converges to a constant. So the decomposition that we are using is basically the limit of the eigenfunction, a constant, plus something that's orthogonal to this limiting eigenfunction. And well, this strategy might also be applicable to other cases. For instance, this strategy is also applicable if we have a positive instead of a negative alpha. When we did this, we've been a little bit surprised that almost the same idea works for positive as for negative alpha, because traditionally the two regimes for alpha is positive and negative require different proof strategies. But there's only one small adjustment we have to make to the proof, and that is instead of defining h as the mean of u, we define h as the mean of u over the boundary of omega, and then w would be a function that vanishes if we integrate it over the boundary, and everything else is almost the same. So if we do this, we obtain the following lower bounds for the first eigenvalue of the P-Laplace operator if alpha is positive. Once again, we can define a constant c. It's not exactly the same constant as on the previous slide, but it has the same structure. It's the supremum over the over all functions w, such that w integrated over the boundary of omega vanishes, and we take the supremum of w to the p integrated over omega divided by the gradient of w to the p integrated over omega, and then we get lower bounds that have the same structure as in the previous case. So lambda 1 is bounded from below by alpha times the perimeter of omega divided by the area of omega, minus a term of the form alpha times alpha to the power of 1 over p minus 1 times a constant, and exactly the same works if p equals 2 and if p is between 1 and 2 as well. All right, so these are the results that we obtained for bounded domains. And for unbounded domains, the setting is quite different. Obviously, this strategy here does not work for unbounded domains, especially if we have a domain which is a complement of a compact set, because a constant function is no longer integrable if we have an unbounded domain. So the situation is completely different. And initially, I had the plan to tell you something about the unbounded setting as well. But since I've spent a little bit more time with the first part than I expected, I will skip a few slides. And instead, I would like to show you another application on bounded domains, which is what hopefully explains the simulation that we've seen in the background of the title slide. So this application concerns a boundary catalytic branching process, and this process was described in a paper recently by Grebenkov and Yi, published in the year 2026, and they consider the following stochastic process. They have a domain, omega, and as always, omega is a subset of Rn, and the boundary is at least Lipschitz continuous, and the boundary can be decomposed into three parts: the absorbing, the catalytic, and the reflecting part. So the boundary of omega can be written as the disjoint union of gamma A, gamma C, and gamma R, where gamma A is the absorbing part, gamma C the catalytic part, and gamma R the reflecting part. And then they consider almost the same stochastic process that I mentioned before. They have a Brownian motion inside of omega, and when a particle hits the boundary, on a segment which belongs to gamma A, then particles are absorbed at a certain rate. If they hit the boundary on a part that belongs to gamma C, particles are created at a certain rate, denoted by QC. And if the particle hits the boundary on the reflecting part, then particles are simply reflected. So here we can take a look at this simulation. We start with 10 particles. I've chosen QC to be 0.04. So QC is related to the rate at which we create particles. And the catalytic part is just this arc that's marked in green right here. This red arc is the absorbing part, and here we absorb particles at a rate 0.06. Well, actually 0.06 is not exactly the rate, but there's a one-to-one correspondence between QA and the probability at which we create particles. And here you can see the number of particles that are currently in the disk and how many times we created new particles and how many times we've killed particles. And now we can play around with the two parameters QC and QA a little bit. You can see currently we are still at 10 particles, which is where we started. Now it's going down a little bit. So here it seems like the number of particles is almost constant. It might go down a little bit. But now if we increase the rate at which we create particles, then of course the number of particles will increase, or the number of expected particles will increase. Well, this is what's going on right now, and it's increasing quite heavily. So maybe let's put this down a little bit. And then if you increase the rate at which we absorb particles, then the number of particles should go down again, which is happening right now, and so on. And as before, the expected number of particles inside of the domain omega can be related to eigenvalues of the following eigenvalue problem. To be precise, the mean population at time t behaves as e to the power of negative lambda 1 times t, where lambda 1 is the first eigenvalue of this eigenvalue problem right here. It's almost the same as before, but the main difference is that alpha is no longer constant on the boundary, but piecewise constant. So in omega, we still have the PDE that the Laplacian of u plus lambda times u has to be 0. On the absorbing part of the boundary, we have a boundary condition of the form the partial derivative of u in direction of the outer unit normal plus something positive times u has to vanish. So this would basically correspond to the case where alpha is positive from before. On the catalytic part, we have something like the derivative in direction of the outer unit normal minus a positive constant times u vanishes. So this would mirror the case where alpha is negative. So here we create particles, and on the reflecting part of the boundary, we just have Neumann boundary conditions. And I would like to mention this result because even in the setting where alpha is no longer a constant on the boundary, but piecewise constant in this case, we can still apply the same idea, the same decomposition method that we used before to find lower and upper bounds for the first eigenvalue. If we do this, we obtain the following result. An upper bound, once again, is obtained by just inserting a constant trial function into the variational characterization. So previously we had alpha times the perimeter of omega divided by the area of omega. Here this changes to QA times the length of gamma A minus QC times the length of gamma C divided by the area of omega. And the lower bound is obtained using the same decomposition method as before. And well, the first term of the lower bound is the same as in the upper bound. And then we have a certain remainder, which, well, previously the remainder was of the form alpha squared times the constant. Here we now have, instead of alpha, something like QA times the square root of the length of gamma A plus QC times the square root of the length of gamma C squared. So once again, when QA and QC are close to 0, then lambda 1 basically behaves as this expression right here. So maybe let me restart the simulation with a setting of the variables that's a little bit more interesting. So when QA and QC are small, or when they are small and close to each other, in this setting QC is a little bit larger than QA, and the length of gamma C is the same as the length of gamma A. So in this case, we would expect that lambda 1 is negative, but still close to 0. So if lambda 1 is negative, we have an exponential growth of the number of particles. And hopefully this is also what we can see right here. We started with 10 particles and now it's going up. So this would be one setting where we can still apply the decomposition method that I mentioned before. And The next natural step would be to try to apply the same method if alpha is not piecewise constant, but maybe just a general function defined on the boundary. And then the question, what happens if alpha tends to 0 in a suitable norm? And even in this setting, we can apply some of the methods that we used before. However, we are still working on this, so I cannot show you any of the results. And well, I think with that, I'm basically done for today. So if you do have any questions, please feel free to ask. And thank you very much for your attention so far.
Are there any questions?
You didn't say anything about exterior problem, but let me just a second ask a question about the exterior problem. So how basically you formulate it? So for a linear problem, you don't have usually eigenvalues, right? So
Well,
it's an essential spectrum, you know.
But it's not purely essential.
What there might be, but yeah, I agree. There might be, of course, but there might be no. So then, how you formula what's the situation in nonlinear? What's the nonlinear situation?
Yeah, maybe let me show you one or two slides that we have. Okay, our setup is that the exterior domain is always the complement of a compact set, and we have Lipschitz boundary, and we're still interested in finding lambdas such that there exists a function u such that lambda and u solve this PDE right here. Now, in the bounded setting, we always define the first eigenvalue by this variational principle. For unbounded domains, this is not necessarily an eigenvalue, because even if we talk about the classical Laplace operator, this lambda 1 might belong to the essential spectrum instead of the discrete spectrum. And in this case, we cannot guarantee that there exists an eigenfunction associated to the lowest point of the essential spectrum. However, what's true for the classical Laplacian is that the essential spectrum is always given by the interval from 0 to infinity. So as soon as lambda 1 is negative for the classical Laplace operator, we know that it's not part of the essential spectrum, therefore it is part of the discrete spectrum, and then we know that there exists an associated eigenfunction. And something similar is true if we talk about the P Laplace operator. Here we can define the same quantity just as an infimum, and first of all we can show that this is always non-positive. This is a straightforward proof. And then if it is strictly negative, we can show that it is an eigenvalue. This just follows by standard methods, take a minimizing sequence, show it converges, and so on. And well, if it's negative, it's an eigenvalue, and this is basically the only case that we're interested in. So one of the first questions would be, when is lambda 1 negative? And this, of course, depends on alpha, on p, and on the dimension, and maybe even on the geometry of the domain omega. And then whenever lambda 1 is negative, we know that it's a well-posed problem, and in this case we can try to find, for instance, isoperimetric inequalities or other lower or upper bounds. And this is the thing that we did in the second part of the paper. If you want, if there were no other questions, I could tell you a little bit more about this, but...
There is a question.
I was just asking about the lower bound. Is there like a conjecture what would be the sharp estimate? Because when I saw it first time, I wasn't sure what it's like sharp or so this constant that it's like, is there like some quantitative dependency?
I'm pretty sure that the constant is not sharp. However, I do think that the order of the remainder is the correct one. For the classical Laplacian, that's definitely something like alpha squared that we expect here. For the P Laplace operator, it should also be something like alpha times alpha to the power of 1 over p minus 1. But I would say the chances that the constant is sharp are slim to none.
So is there like some simulations done on some domains, like
yes,
ellipsoids? Or,
yes, we tried some ellipsoids, we tried some rectangles or other simple properties of this type. And even in the proof, if p equals 2, this constant is not the same as this constant right here, because we have to make some estimates. So the constant, there's no way that the constant is sharp. But I think the order is the correct one.
concerning this constant C here, it looks suspiciously like it ought to be something like a reciprocal first non-trivial
Steckloff eigenvalue?
well, no, because it's integral over omega, not over the boundary. It looks like it should be the first non-trivial Neumann P Laplace eigenvalue, or the reciprocal of it.
Yes, I think for the first theorem, when alpha is negative, this can be related to Steckloff eigenvalue in the sense that you mentioned. For positive alpha, it might be related to the Neumann eigenvalue instead. Yeah, I should check this carefully, but I would say if p equals 2, I'm pretty sure that this constant here can be expressed in terms of a Steckloff eigenvalue, and probably this constant here can be expressed in terms of a Neumann eigenvalue, and most likely this is valid for any p. I think so, yes. And this might also answer the question whether there are any known estimates. So maybe we can just use some estimates that are known for the Steckloff or the Neumann eigenvalue, but as I said, we haven't really investigated this.
So what happens to the higher P Laplace Roman eigenvalues goes to plus infinity?
Well, in general, I would say I have no idea, and I don't think that it is known. For the classical Laplace operator, that should be known. I'm pretty sure that this is known. For the P Laplace operator, we first of all have to answer the question whether the second eigenvalue is variational or not. And if it's not variational, then none of the methods that we are using work at all. So I would think that this is an open problem. I would be really surprised if there is a known answer to that. At least I'm not familiar with any positive result.
Might be something in 1D, I guess, but you're doing dimension 2 and higher.
Into a problem that's eventual.
Any more questions? No, that's thanks. Speak again.